Hello and welcome to our presentation for the Software Evolution and Maintenance subject. For this assignment, our group has chosen to analyze the paper titled Slicing Object-Oriented Software, which was authored by Larsen and Mary Jean Harrold from the Department of Computer Science at Clemson University. Our team consists of 5 members: Rohan, Justin, Joshua, William, and Marcus. Together, we have broken down this paper to examine how it addresses the unique challenges of applying program slicing techniques to the object-oriented paradigm. We will begin by looking at the motivation behind this research.
Let's start things off with the motivation of the work. Firstly, slicing is very useful, but mostly for procedural code. The paper begins by reminding us that program slicing is a very powerful analysis technique. It plays an important role in debugging, program understanding, testing, reverse engineering, and metrics analysis. Earlier foundational work by Weiser, by Ottenstein, and by Horwitz, Rebs, and Binkley defined what slices are and showed us how to compute them using data flow analysis and system dependence graphs, or SDGs. These approaches were especially effective for procedural languages like C. Interprocedural SDGs, combined with the two-pass graph reachability algorithm of Horwitz and colleagues, can compute very precise slices across procedure calls. They achieve this by modeling parameter passing and by introducing summary edges to preserve calling context. However, there's a big limitation here. These classical representations and algorithms were built with procedural concepts in mind, things like procedures, function calls, and global variables. They were not designed to handle the key object-oriented concepts such as classes, instances, inheritance, or dynamic dispatch. Secondly, existing object-oriented work is incomplete. Some researchers had started extending dependence graphs for object-oriented languages, or had added features like exceptions or modules. But the key point is that none of the existing work had provided a complete, precise, and practical SDG-based slicing framework that handled all major object-oriented features together. In other words, only partial pieces existed. Nobody had solved the full problem in a way that was both theoretically correct and workable in practice. Thirdly, object-oriented features make representation much harder. One of the reasons for this gap is that object-oriented features complicate program representation dramatically. Think about it. It has instance variables which form the object's internal state, and it has methods which operate on that state. Unlike global variables in procedural code, instance variables are not directly visible to callers, but they persist across method calls. This means that there are many hidden data dependencies across calls, dependencies that must still be captured for slicing to be correct. A representation must model these dependencies even though the variables are encapsulated and not directly accessible from outside. Dynamic dispatch adds another layer of difficulty, because the actual method invoked at runtime may depend on the concrete type of an object. All these features mean that the familiar models used for procedural slicing simply don't extend smoothly into object-oriented languages. Finally, object-oriented development styles creates extra needs. In addition to language complexity, there are also the way object-oriented systems are developed. Classes and libraries are often designed and tested long before the final system is assembled. This means we frequently need to slice incomplete systems, perhaps just a single class, or a group of interacting classes, or even a reusable library that will be later incorporated into larger applications. Because of this development style, we want dependence graph representations that can be built incrementally and reused. Once we build the dependence graph for a class, we should be able to plug it into different programs and larger systems without reconstructing everything from scratch. This saves both time and money and also supports modular analysis, which is one of the major promises of object-oriented design. So, to conclude, the motivation, the authors want the strong benefits of SDG-based slicing to work together with modular, reusable style of object-oriented software engineering. They are aiming for a framework that is both theoretically precise and practically scalable, specifically tailored for object-oriented systems. Now, given all the challenges I previously stated, the problem can be stated simply as follows. How can we define a reusable, scalable system dependence graph representation for statically typed object-oriented software such as C++ that supports precise and efficient interprocedural slicing, handles the full set of object-oriented features like classes, inheritance, polymorphism, and encapsulation, and works for both complete applications and incomplete systems such as individual classes or class libraries. In more concrete terms, the paper asks, how can we define a dependence graph representation for individual classes? How can we extend this representation to derived classes and inheritance hierarchies? How can we model interacting classes and object instantiation? How can we support polymorphism and dynamic dispatch within SDG? How can we slice incomplete object-oriented systems such as isolated classes or libraries? How can we construct SDGs for complete programs by combining the main routine with class representations? And finally, how can we ensure that the representation is space efficient and practically reusable, something that works in real software development workflows? In summary, the motivation highlights the gap between classical slicing methods and modern object-oriented software. The problem statement defines the need for a complete modular precise framework that integrates object-oriented features into system dependence graphs in a reusable and scalable way.
Moving on to section 2, I'd like to walk you through the research objectives of this paper. At a high level, the authors had one primary goal: to construct system dependence graphs that are specifically tailored for object-oriented software. But to make this actually work, they targeted 3 specific areas shown here. First, they focused on what we can call the efficiency gap. In the introduction, the authors argue that an efficient graph representation for object-oriented software should consist of a class representation that can be reused. They identified that minimizing construction costs via reuse was essential for the technique to be practical. Second was the completeness gap. Traditional slicing usually relies on a complete executable program, but in the real world, developers often work on incomplete systems like isolated libraries or single classes. The authors wanted to make it possible to slice these isolated parts by simulating the environment around them. And finally, they needed to ensure that the graph could be accurately handle the unique complexities of object-oriented code, specifically features like inheritance and polymorphism, which existing techniques did not adequately address. Let's dig a little bit deeper on how they plan to solve this. The core problem was that existing slicing techniques were designed for procedural languages, so they didn't adequately define dependence graphs for the full range of object-oriented features. So the objective wasn't just to use existing graphs, but to define a new graph representation. While they built upon the standard system dependence graph, the specific contribution is something called the class dependence graph, or CIDG. Think of the CIDG as a modular building block. It's a specialized graph designed to model a single class, capturing all of its dependencies in isolation without needing to know the calling environment. This modular approach allowed them to tackle those 2 practical objectives that I've mentioned earlier. Let's take a look at the reuse objective first. One of the biggest issues with slicing is the computational cost. To fix this, the authors designed the graphs to be incremental. The idea is simple. You analyze a class once to build its CIDG, save that graph, and then reuse it whenever that class is inherited or instantiated elsewhere. This avoids the need to recompute the analysis every time. And then we have the incomplete system objective. As I mentioned, developers often write code that isn't ready to run yet. To handle this, the authors created a frame. This acts like a simulator. It wraps around a single class and pretends to be a calling program. This allows you to slice a single class in total isolation without waiting for the rest of the system to be written. In summary, the author's primary goal was to redefine the system dependence graph to explicitly support object-oriented features like inheritance and polymorphism. They achieved this by introducing the class dependence graph, a modular structure designed specifically to enable efficiency through reuse and the analysis of incomplete systems.
Building on what William discussed about the research objectives, I'll now walk you through the novel contributions this paper brings to the field. The main contribution of this work is a comprehensive representation framework for slicing object-oriented software. While programming slicing existed before this paper, existing techniques couldn't quite adequately handle the full range of object-oriented features. So with that being said, what exactly makes this paper and this work specifically novel? Well, firstly, the authors introduced the class dependence graph, or also known as CI/DG. This is a new graph structure specifically designed to capture control and data dependencies within a class without needing to know how the class will be called. Each method in the class gets represented as a procedure dependence graph, and these are connected through a class entry vertex. This is significant because it means you can analyze a class in isolation. Secondly, the paper provides a solution for handling incomplete systems. In real-world software development, we often work with individual classes or class libraries before the full application actually exists. So in doing so, the authors solve this by introducing what they call a frame. Essentially a universal driver that simulates all possible sequences of calls to a class's public methods. And in 1996, this was genuinely new at the time. Secondly, or should I say thirdly, they address polymorphism through something called a polymorphic choice vertex. When a method call could go to multiple destinations at runtime, this vertex represents that dynamic choice in a static graph. So all possible destinations are included in the representation. Fourthly, and perhaps most practically important, their approach is designed for incremental construction and reuse. When you build a derived class, you don't rebuild everything, right? You reuse the analysis from base classes. So this directly mirrors how object-oriented development works and makes the technique actually scalable. And finally, they demonstrate that slicing and slices can be computed on these graphs using an existing efficient two-pass algorithm, which means they didn't need to invent new slicing algorithms. Yet their contribution is a representation that makes existing algorithms applicable to object-oriented code.
Thanks, Joshua. So now that we've seen what the paper contributes, I'll be walking us through how the authors actually developed and validated their approach. The methodology behind this paper follows a design and development research, or also known as DDR approach. So in simple terms, the DDR is used when researchers want to build a new artifact to solve a clearly defined problem, and then explain and evaluate that artifact in a systematic way. So in this paper, we see that the artifact is the new system dependence graph, also known as SDG representation, for object-oriented software, together with a slicing algorithm that handles classes, inheritance, and polymorphism, all of which are concepts of object-oriented programming. The author doesn't just propose the representation, they also analyze its structure to reason about its efficiency, and then finally also demonstrate it through a real-world C++ system implementation. So at a high level, the methodology moves through the DDR sequence in the following ways. It first starts with a concrete problem in existing slicing techniques, so it addresses the gap in the research, and secondly, it designs a new representation to address that problem. And then following that, it evaluates it analytically and empirically before reflecting on how broadly the applications and findings can be used across the field of software engineering. So moving forward, I'll be actually covering in greater detail the research steps and how each one builds on evidence about this representation and makes it both a sound and practical application. So now I'll be explaining a bit more on the individual steps of the research of this paper, which actually follows the DDR flow quite closely. So I'll be explaining them in a bit greater detail and identifying how it mimics the DDR flow. So in step 1, we begin right off the bat with the authors identifying and justifying the problem. The issue here was that there was a gap in traditional slicing techniques that worked well, mainly for procedural code. But the struggle we saw was that object-oriented features like inheritance, polymorphism, and interacting classes wasn't fully addressed. In fact, there wasn't a complete, precise, and practical SDG-based framework that covered the full range of OO features, especially for incomplete systems such as class libraries. And we see that this is the technical gap that the authors first identifies. And through this problem, we can see that the second step that they do is to specify the objectives and design requirements that will be seen throughout the paper. In fact, these requirements that are specified directly mirror the research objectives that William had described earlier. And in terms of the OO representation that they wanted to have, the few key things that they highlighted was, firstly, it had to support efficient interprocedural slicing, and following that, it also had to work on complete programs and incomplete programs, for example, the individual classes that don't really have a main method yet. And we can see that after the authors had specified the objective and design requirements, in the third step, they moved to designing and developing the actual artifact. And here is where we see things such as the class dependence graph, the CIDG, and eventually the full SDG, the system dependence graph, being fully developed for OO systems. And the key idea here is that they had designed all these things based on the specifications stated earlier in step 2. After completing the development work on the artifact in step 3, well, the fourth step would be to perform an analytical evaluation for both efficiency and scalability. Instead of just claiming that the graphs are functional or that they are practical, the authors actually derive an upper bound on the size of the SDG based on parameters such as the vertices and edges per method, instant variables, call sites, and even the inheritance depth. This analytical quantitative analysis allows them to argue that even in the worst case, the graph size remains in a manageable range. And in the fifth step, they demonstrate the artifact empirically. So this is done by constructing a C++ program, which is with over 9 classes, 65 methods, and an inheritance hierarchy of up to 3 levels deep. This example shows that the representation and slicing algorithms are not just theoretical, but they can be actually implemented with a reasonable size OO system. And in the sixth step, as the paper closes, the sixth and final step, the authors actually reflect on the artifact's applicability. In fact, they also argue that the same approach is not limited to C++, but can also be applied to other statically typed OO languages, for example, Java, C#, or even ADA95. And what this allows is that it positions the work as a general framework for OO slicing rather than just limiting it to a framework for a single language. So overall, the methodology is one that defines a clear gap. And what it does with that clear gap is through objectives, all those, it guides us all the way to positioning the paper as a reusable language-independent representation backed by both theoretical analysis, but also a concrete implementation through the empirical example of the C++ OO system. And that's the research methodology of the paper. For the next part, I'll pass it on to Marcus to talk about the research methodology evaluation criteria.
Right now, I'll be talking about the evaluation criteria for the research methodology. There are 3 criteria to be made when we're evaluating research methodology. The first criteria is structural evaluation. In this evaluation, we evaluate if the representation done in the research is able to properly handle object-oriented features correctly. These features include the base classes within a program, the derived classes within the program, which is inheritance and reuse of class representations, interacting classes, which is basically how classes instantiate each other and also call each other, as well as polymorphism, which is dynamic method calls with multiple possible destinations. This criteria also evaluates if the representation is able to handle different system types. These system types being incomplete systems, which are object-oriented programs that are not yet completed, and for example, like there's only a single class done, or there's a class library with no full main program, as well as complete systems, which are, like it says, full, complete, object-oriented program systems. The next criteria is algorithmic evaluation. This evaluation basically talks about whether the slicing algorithm used to compute the slicing of a program is correct or not. So we have to evaluate their slicing criterion as seen here, P and X, where P is a statement and X is a variable and method call. And in X, we also have to verify whether it's correct, whether the variable handling as well as or the method call handling is properly defined and used. We also need to make sure if the accuracy is correct or not in order to properly evaluate if the slicing of the program is proper. The last criterion is efficiency evaluation. In this criteria basically discusses whether the representation done within the research is scalable and practical. So in order to evaluate this, we have to look at the size of the SDG, for example. So we need to take into account vertices per method, edges per method, parameters per method, global variables, instance variables, call size per method, inheritance depth, and total methods in order to calculate the size of the slicing or SDG. And if it's too large, then it's not exactly scalable and practical.
Moving on to section 5, let's define the boundaries of this research. The authors limit their scope specifically to statically typed object-oriented languages. While their primary focus in the paper is C++, they note that the concepts apply equally to languages like ADA95. The analysis type here is purely static analysis, meaning the slicing is performed by analyzing the code structure without actually executing the program. With that in mind, let's dig a little bit deeper into the language scope. It is important to emphasize that this technique is specifically designed for statically typed environments. This explicitly places dynamic languages like Python or JavaScript outside the scope. The technique relies on the compiler's ability to provide type information, which allows us to limit potential method calls much more effectively than in dynamic environments. In terms of features, the authors focus on the specific challenges introduced by object-oriented design. They address how to preserve the state of an object between method calls, but the biggest challenge they tackle is polymorphism. They solve the issue of dynamic binding, where the destination of a call is unknown until runtime, by creating a graph that maps out every statically possible destination to ensure the slice is complete. This work operates at 3 distinct levels of granularity: individual classes, groups of interacting classes, and complete programs. This distinguishes it from traditional techniques that typically requires a full running application to work. However, they explicitly exclude detailed analysis of aliasing and arrays. Their argument is that existing techniques for procedural languages already handle these issues effectively, so they can be integrated without needing to be reinvented here. Finally, looking at this diagram, we can infer why they insisted on that static typing constraint. The technique relies on building a graph of all possible paths using a polymorphic choice vertex, shown in the red box. In a statically typed language, the compiler gives us a short list of destinations. If we tried this in a dynamic language, the vertex would technically have to connect to almost every method in the system, which would make the graph and the slice uselessly large. In short, the scope is strictly defined by static typing to keep the graph manageable, while offering a flexible granularity that allows developers to slice single classes in a way previous techniques could not.
Now I'll be moving on to section 6.1, where we'll highlight what the paper actually found. The first one being about the size and scalability of the graphs. Using the analytical model, the authors estimate a theoretical upper bound of about 282,112 vertices initially. However, when they actually built the graph for that particular C++ system with 9 classes and around 65 methods, the real SDG size was only 1,257 vertices. This sort of gap between the worst case bound and the observed size is a strong indication that the technique is proven to be not just mathematically possible but also practically feasible. The second part of the paper actually talks about the combination of CIDGs and SDGs. This combination actually allows representation of the base class, the derived class, and even interacting classes. Following that, it also correctly models polymorphism and dynamic binding, polymorphism being one of the OO concepts that was talked about earlier. And also the last one is that it supports slicing for complete and incomplete programs. So this includes single classes or class libraries without a main program. So in other words, this meets the exact requirements that had been set out earlier in the objectives. Therefore, this in a way proves a successful correlation between the objectives and the research findings. These findings translate into 3 layers of significance. First, the technical significance covers on the long-standing gap by providing an SDG-based slicing approach that works for the full range of object-oriented features. So this includes classes, inheritance, polymorphism, and even dynamic binding, all done within a single unified framework. The second layer is the practical significance behind this paper. Because graphs are reusable and efficient to compute in practice, they actually enable scalable slicing for OO languages like C++ and even ADA95. This directly supports the real software engineering tasks like, for example, debugging complex OO systems, understanding legacy code, and even performing impact analysis during maintenance and evolution. The third layer is the research significance. The authors don't just start from scratch or throw away existing theories, but they build on classical procedural SDG work and extend it to OO without redesigning everything from scratch. This does mean that future research on program analysis can reuse this framework as a foundation instead of reinventing a new representation for each language or paradigm every single time. Well, so to summarize, the methodology led to representation that is expressive enough to capture complex OO behavior, but also efficient to be practical on real-world systems and general enough to influence future work on object-oriented program analysis. So now I'll hand it over to Rohan to actually guide us through the applications of these findings.
Now, there are applications of this work such as debugging object-oriented programs, program comprehension, regression testing and change impact analysis, maintaining and evolving object-oriented systems, re-engineering and reverse engineering of object-oriented code, security, privacy and data flow analysis, dead code detection and feature modularization, better developer tooling for IDEs and static analysis tools, and metric quality analysis for object-oriented design. But I will focus on 2 specific applications: debugging object-oriented programs and program comprehension. First, let's talk about debugging. When an object-oriented program produces an incorrect output, slicing can be extremely powerful. With this framework, we can slice with respect to a particular instance variable at the point of failure, a method's output, or a specific return value. The key is that the class dependence graph models instance variables as shared state across methods. That means all hidden data dependencies through fields are captured automatically. Even though instance variables are encapsulated inside classes, the slicing system still tracks their influence across method boundaries. The extended system dependence graph adds another layer of strength by handling dynamic dispatch. If a call can invoke several overriding methods, the slice includes all the correct possible implementations. This ensures that polymorphic behavior is captured precisely. Constructors, destructors, and interactions between objects are also part of the dependence graph. As a result, initialization bugs and shutdown problems become visible in slices, instead of remaining hidden inside constructors or hidden state transitions. The end result is that when debugging object-oriented code, instead of manually scanning through an entire class hierarchy, you get a focused cross-class slice that respects inheritance and polymorphism. This significantly reduces debugging time and effort. The second major application is program comprehension, simply understanding how an object-oriented system works. Developers often ask questions like, where does this field such as balance get changed, especially across all subclasses? Which parts of the code update the UI when a certain event occurs? What influences this particular method's behavior? Using slices, we can answer all of these questions by slicing with respect to a field at a specific point, a public method of a class, or an observable behavior we care about. The class dependence graph and extended system dependence graph provide a representation that aligns neatly with object-oriented concepts, classes, methods, fields, and inheritance. Because the representation is modular, we can choose the scope of our understanding of a single class, a small cluster of interacting classes, or the entire system. We simply choose which dependence graphs to connect together. Another major benefit is the ability to slice incomplete systems, which is extremely common when working with libraries or frameworks. The authors integrate a concept called a frame, which allows slicing even when there is no main program yet. This is essential when studying reusable components in isolation. For example, when examining an API, a class library, or a framework, there's no concrete driver code. In conclusion, for new developers or even experienced ones joining a project, slices become an incredibly valuable learning tool. Instead of just forcing someone to read an entire code base, we can show them a minimal, precise slice that answers a specific question.
Now, let us discuss the strengths and advantages of this work. The first strength is that this paper directly addresses a real gap in literature. The paper clearly identifies that no existing techniques adequately handled object-oriented features, specifically for program slicing. And at the time of publication in 1996, C++ and other OO languages were becoming dominant, so this was highly relevant work addressing a genuine need in the software engineering community. The second strength is that it was practical and efficient through reuse. One of the biggest strengths is the emphasis on reusability. The authors designed their system dependence graphs so that class representations can be computed once and reused many times. For derived classes, you inherit the analysis from the base classes and only compute what's new. So this mirrors exactly how OO development actually works. And the authors acknowledge that, if I may quote, that most applications reuse components, and it is possible to analyze a component once and reuse the analysis information many times. The third strength is that it handles incomplete systems. This is particularly a strong point because most prior work on program slicing assumed you had a complete program. But in practice, we develop and test classes independently, right? So the frame concept allows developers to compute slices on individual classes or class libraries. This was especially useful for understanding and debugging and even testing components specifically in isolation. The fourth strength is that it had a solid theoretical foundation. The paper builds on well-established work, particularly on Horwitz, Reps, and Binkley's system dependence graphs, and their two-pass slicing algorithm in the paper they wrote back in 1990. By extending proven techniques rather than starting from scratch, the authors ensure that their work is on solid theoretical ground, which is vital in software engineering. The next strength is clear examples throughout. The paper uses a running example with an elevator class and an alarm elevator derived class. This makes the concepts tangible and easier to understand. The figures clearly show how the graphs are constructed and how slices works on them, which is important for new readers to understand. The sixth strength is actually the preliminary size analysis. The authors don't just propose a technique, they analyze its space requirements. They provide equations for estimating SDG size and conduct a small case study showing that actual graph sizes are much smaller than worst case bounds. For their 9-class example, the upper bound was over 282,000 vertices, but the actual SDG had only about 1,257 vertices, which is pretty impressive if I may add. And the final strength is their language applicability. While the paper focuses on C++, the authors note that their techniques apply to other statically typed object-oriented languages, like Ada 95, so this broadens the potential impact of their work substantially. And with that being said, these strengths collectively make this a well-rounded contribution that address both theoretical and practical concerns.
Now I'll be talking about the weaknesses and limitations within the research paper. The first of these weaknesses is the assumption of prior algorithm knowledge. So within the paper makes reference to an algorithm called the two-pass graph reachability algorithm that helps to calculate the slicing of a program. But however, although they mention it, they never explain what this algorithm is, nor do they explain the workings behind or the formula of the algorithm. So it assumes that we already know what this algorithm is, but for readers who don't know what this algorithm is, it may lead to confusion. The second weakness is that incomplete systems are not fully illustrated within the paper. So while the construction for single incomplete class programs is clearly shown and explained within the paper, the procedure for multiple interacting incomplete classes within an incomplete system is less explicit, and there is no figure that shows and explains how this slicing may work within an incomplete system. So this will lead to ambiguity to the reader and may cause confusion later on. The third weakness is a limited language scope. It is stated explicitly that the paper basically covers slicing for statically typed object-oriented languages. However, it does not cover dynamic languages at all, such as Python. So it is less general and more specific to a single type of language, object-oriented language type, which is static languages. The fourth and final weakness of the paper is its presentation and readability. The fonts that is used to write the paper is quite small, and it's also the line spacing is not that big, so the words look very close to each other and it may be hard to differentiate lines from each other. Another example of this weakness will also be the figures shown within the paper. The figures are dense with call lines between nodes, and each call line is also of a difference. It can be of different boldness. It can be a different way of drawing the line. In the end, it can be very hard to follow. And while it's not theoretical, while the figures are not theoretical in nature, it still leads to confusion for readers.
This brings us to the end of our presentation. On behalf of the entire group, Rohan, Justin, Joshua, Marcus, and myself, I would like to thank you for your time and attention. We hope this analysis has provided a clear insight into the work of Larsen and Harrold. Thank you for watching.